Hello and welcome. This is AQA A2 Unit 5 June 2016 past paper. Okay, so this is question number 2 and this question is all about radioactivity. Okay, so the first question says the exposure of the general public to background radiation has changed substantially over the past 100 years. State one source that has contributed to this change. Okay, now there are many different lists. There's many different examples here in the mark scheme, but the one that I would most commonly use is radioactive waste from power stations. An increase in that, because an increase in technology to be able to develop radioactive power stations. So obviously there's going to be more waste from that. So that's the first thing I would state. But obviously there are many other examples, such as nuclear medicine, nuclear accidents, such as Chernobyl, and obviously more testing of weapons and stuff. But as I say, nuclear waste will also be acceptable. You don't need to explain anything, the reason behind it. Okay, it's just only worth 1 mark, so just a factor. Okay. The next one is a bit more technical. Okay, so basically what we've got here is a setup of a radioactive experiment. Okay, so we've got a source, a radioactive source, and it's placed 0.15 meters from the detector. Okay. And we're told that it has a background count of 40 counts per minute. Okay. And at this particular separation, the total counts that's detected, okay, is 2050 per minute. Okay, so let's just have a quick think about what's happening here, what's actually being detected by this detector. Okay, they've seen it. So the total count is 2050 per minute, but that's not just coming from the source, that's also coming from the background radiation. So 40 counts of that is background. It's background radiation, because obviously you're not going to ignore that, that's included in the counting as well. And then obviously the remaining 2010 counts is from the source. Okay, so obviously we're going to be using some kind of the inverse square law of radiation. So the student obviously has nothing else to do with his life, moves the detector further away from the gamma source and records the count rate again. Okay, calculate the average count rate you would expect when the new distance is 0.9 meters. Okay, so that's the workings at 0.15 meters. What's the reading at 0.9 meters? Okay, so what we need to do here is use the count rate from the source. Okay, as the intensity is also known as the count rate. Okay, per whatever division of time you're looking at, in this case minutes. Okay, so what we're going to do is split it up into before and after situation. Okay, so this is, I'm going to label as the initial distance x1, okay, is 0.15 meters, and at that initial distance x1 we receive an initial intensity of 2010 counts per minute. Okay, so therefore at this new distance of x2 0.9 meters, what is now the intensity? Okay, I2. Okay, so we're going to be using I equals k over x squared, okay, and comparing the two. Okay, so if we put our numbers in, okay, so I1, if we're using I1, okay, is 2010 counts per minute over the constant k over the distance of 0.15 squared, okay, and the I2 is going to be, we don't know that, is k over the distance squared, 0.9 squared. Okay, so what, because we could either work out what k is here and then put it in here and work out what I is, but an easier thing to do would be to make them both give subjects of k. So k is equal to I2 times 0.9 squared. Okay, and we'll call that equation 2. Equation 1, k is equal to 2010 times 0.15 squared. Now I could work equation 1 out and work out what k is, okay, but what I'm going to do, just to show you where we're getting these figures from, is keep them uncalculated, so to speak. Okay, so now, because equation 1 and 2 are both equal to k, we can say equation 1 is equal to equation 2. So, therefore, 2010 times 0.15 squared is equal to I2 times 0.9 squared. Okay, so in that case, we want to know what I2 is. So I2 is equal to 2010 times 0.15, okay, over, obviously 0.15 squared, over 0.9 squared. Okay, so that will give you a figure for I2, which should be 56 counts per minute. However, that's not the end answer. Because we've taken away the background radiation to work out this new distance, okay, we need to now add in the original amount. Okay, so it's 56 plus 40, so therefore it's going to be about 96 counts. Okay, so hopefully that makes sense. That's what the new figure will be. You had to take this 2010 instead of using the 2050, otherwise it would give you a different answer, okay? Because we have to take out the background radiation because it's not from the source, so this 40 counts per minute, you will still record if you move the distance billions and billions of meters away, okay, obviously assuming you're still on Earth, which you won't be, it's just exaggeration, okay, but if you use 2010 as the 2050 as the intensity for 1, okay, instead of 2010, which is probably where you would have slipped up on this question, okay, what you're saying there is that the background radiation is affected by distance, when it's not, okay, the only thing that's affected by distance is the radiation from the source, okay. The background radiation will always be around the detector. Okay, so as far as we're considering this question, you will always at least read 40 counts per minute plus whatever is coming from the source at that given distance. Okay, so that's why we needed to take it out and put it back in. Okay, so you need to remember that in these types of questions. The other way of looking at it as well, they wouldn't have told you the background counts as 40 counts per second if it wasn't relevant in some way. If they'd have just said this is what's received, then you know 2050 counts per minute, and he didn't say anything about background radiation, then fair enough. But because they mentioned background radiation is 40 counts per minute, you're likely to have to do something with that information. And in this particular case, we had to take it out and add it back in at the end of the question. Okay, so hope that guides you. Okay, so that's 2B part 1. So I'm just going to give you a second because obviously I'm going to need more of this space now, so I'm just going to give you a second to copy that down and then we'll crack on with the rest of the question in a second. Okay, so hopefully that was quite self-explanatory for you. I admit I probably got that wrong in the exam because I probably didn't look enough at question counts per minute. Another way they could potentially slip you up is by creating this idea that the times are in minutes and seconds, okay, so 96 times per minute, and they might give you one in seconds, so just remember to make sure all the time is exactly the same for the intensity, okay, because obviously you wouldn't times 50 meters per second by 60 minutes and say that's the answer, okay, you know, just another example. Right, okay, so the next part, 2b part 2, it says the average count was 2050, determined over a period of 5 minutes. Okay, explain why the student chose to record for longer than 5 minutes when the separation is 0.9 meters. Okay, so this question is asking you, why is it better to record a longer time, okay, for a longer distance? Okay, so the obvious thing you might think is, well, if it's a greater distance, okay, there's more things to go wrong, so therefore, say, if the count's only, because obviously the further away you move it, the lower the count's going to be, so the greater each count will, so if you record it over a shorter time period, and you recorded an extra count or a different number of counts, each count is going to have a greater effect on your answer. Okay, so say for example if you counted an extra count of radiation at the 0.15 metre distance, an extra plus or minus 1 of 2050 isn't going to make much of a difference, but plus or minus an extra count at 96 counts is going to make a greater difference than at 2050 counts. Okay, so you've got to be careful how you word it. Because the exam in this particular year is very strict on this. You've got to talk about the fact that you reduce the impact of random error and talk about percentage uncertainty. You've got to mention about the fact that it improves the statistics. So in other words, yes, it's right saying the fact that over a greater time period there's less chance for error. However, you've got to specifically say that it decreases the percentage error, okay? And you could reference that to what I talked about before, about mentioning the fact that a plus or minus an extra count at the 96 counts per minute distance is going to have a greater effect than at the shorter distance, okay? And this is because of the fact that there are a greater number of counts, so it will be affected less, okay? But you can't just say it will make it more accurate because it's an increased chance of correct reading. It doesn't really explain quite a lot. Another way of looking at it, okay, instead of, to get into this idea of percentage errors, I'll just write it here as error. And so I'll just write down the answer as percentage error reduced. Slash uncertainty. Over a longer time period. Okay. What was I going to say? Oh yeah, if you think about the equation, the intensity is equal to constant over x squared. Okay. Obviously, in this particular case, you're going to have an error in your intensity and maybe an error in your distance. Okay. So you're not going to have an error in k because it's a constant. You can't have an error in something you don't measure. Okay. So if you think about the error, okay, then you've got the error in I, which is just error in I, okay, over k times 2 times the, over k plus, over 2, sorry, error in I is equal to 2 times the error in x, okay, because obviously you power rule your error, so you do 2 times the error because you're squaring it. Okay, so hopefully that makes sense to you there. But all you need to talk about is the fact that you decrease percentage error or uncertainty over a greater period of time, and that's because at greater distance you calculate less error, so you calculate a lower reading, so obviously that gives you a greater percentage error for each plus or minus that you add or don't add. Okay, so hopefully that explains a bit more. Okay, so 2b part 2 says when the detector was moved to 0.9 meters, the count rate was lower than calculated in B part 1. So it suggests that the source may also emit beta particles. Okay, explain how this can be checked. So what a most common, I think the easiest idea is to think about the cloud chamber experiment, okay? Because it's not, we can put this in any situation we like to enable us to measure this. Okay, so the cloud chamber experiment, if you're not aware of what this is, do research it, but essentially, obviously it's a cloud chamber, so it gives it away really, but it's a gas, okay? You put in a gas, okay, and the amount it's deflected by gives you an indication of what kind of radiation it is, okay? So if it bends more, it's going to be a stronger radiation, okay? So you think of your alpha, beta, gamma, go back to your radiation. So alpha's the most ionising, gamma's the least ionising, so therefore it's deflected the least. So you go through like that. So alpha's deflected the most, beta's the next deflected, gamma's the least deflected. So gamma radiation, okay, is fast moving photons. Beta is electrons, so it's charged, so it obviously deflects downwards, and alpha is the most ionising, so it's deflected the most. That's how you can spot the individual radiation that's being emitted by the source, okay? So if you put the source in a cloud chamber, you could see that it's deflected by different amounts, and that's how you would answer this question. Okay, there are other examples, but I think that's the most prominent, so I'm going to leave it as that. Okay, as I say, there is a mark scheme online, you can check yourself, but thanks for watching, and we'll see you in the next video.